Good evening, and welcome to the Marine Minor Cook Athenaeum. My name is Henrietta Toivonen, and I'm one of the Ath Fellows this year. Viruses cause some of the most terrifying and widespread diseases we know. These tiny particles exist in a gray area between the living and non-living worlds. They are extremely adaptable and inventive in creating strategies to infect other species in their effort to spread and reproduce. They seem to bend the rules of biology and often surprise researchers who are aiming to uncover and understand these pathogens and their disease dynamics. David Quammen, our speaker tonight, is a contributing science writer for the National Geographic, who has traveled extensively to cover a range of issues around the world. He is also an award-winning author of several fiction and nonfiction books, which explore the science, history, and human impacts of emerging diseases. Most recently, he has released 2 short books drawn from his previous work, Ebola in 2014 and The Chimp and the River this year. He has received several awards for his work as an author and journalist. As always, I must remind you that audio and visual recording is strictly prohibited. Please join me in welcoming Mr. Quammen to the Athenaeum.
Thank you very much, Henrietta. And thank you, Schwen, the fellows of the Athenaeum this year. A couple of other thank yous. I certainly thank Priya Junar for inviting me on your behalf to be part of this amazing event. And President Chodosh, I met him last night as Hiram and had a lovely dinner with the 2 of them, hearing about Claremont, McKenna, and this institution, this amazing institution, the Athenaeum. So thank you all for welcoming me. And thanks also, is he still with us, to Chef Dave for this fine food, yes. And making me feel especially welcome by serving Congolese pili pili chicken. I've never gone to give a lecture somewhere and been met with Congolese pili pili chicken, but it's a pleasure. So I am going to talk to you about emerging diseases, where they emerge from, how they emerge, the potential scope of their impacts. Another way of saying that is that I'm going to talk to you about the ecology and evolution of scary viruses. Now, some people would say, do viruses even have an ecology? The answer is yes. Does a virus evolve? Yes. Why should we care? Well, we should care because those facts relate to the possibility that millions of people might die from the next pandemic disease, the next new lethal outbreak of something infectious. And that event, if it happens, will probably be caused by a virus we don't even know about yet. This is a global problem, and it already involves a lot of different viruses in a lot of different places. But over the past year and a half, as you well know, there's been one particular viral disease that has captured the headlines, captured imaginations, screamed out. And that's this one, Ebola virus. Ebola in those 3 little West African countries that were tortured for much of last year and from which the chain of infections is still not quite deleted. And then Ebola in Nigeria, Ebola in Dallas, Ebola in the bad dreams and nightmares of children and of public health officials and of a lot of American politicians. The outbreak became an epidemic, and then the epidemic became an occasion for all sorts of fear-mongering and confusion and xenophobia. The realities of all that going on last year, particularly last summer and fall, this time last year, the realities were bad enough. They were unprecedented in terms of all previous Ebola outbreaks. There had never been an outbreak that had killed more than about 300 people. And at this point, we know that more than 28,000 people have been infected in the West African event as of the latest tally, and more than 11,000 of those people have died. It was all so horrifying and so surprising the way it got out of control in those three countries. And even more horrifying and surprising once it was magnified through the international media, the media in this country and elsewhere, who went just a little bit crazy over the fear and the perceived threat of Ebola. There was too much fear. It's a terrible disease, terrible, horrific virus, but there was too much fear and much too much selfish worry about whether it was going to come and get us. Is it going to get to America? Is it going to come and infect us? And not enough attention to the broader picture. Not enough immediate medical assistance to those three countries in West Africa. Not enough simple material assistance by way of gowns and gloves and viral treatment, pharmaceuticals, and just very, very simple things that can help to stop the spread of Ebola virus from person to person. And the other thing that there wasn't enough of was enough understanding of the virus itself, where it comes from, how it survives between outbreaks, how it occasionally gets into people. Where is virus when it's not killing people? There wasn't enough understanding or even attempts to understand of the larger pattern of which Ebola outbreaks are a part. So that's what I'm going to talk to you about tonight, not Ebola 2014, the public health crisis in West Africa, but that larger pattern. The causal factors, the deeper explanation behind that larger pattern. I want to bring you in just a bit, as I said, on the ecology and evolution of scary viruses. I'm going to take a very straightforward approach. I'm going to define 5 words. I'm going to tell 2 stories, and then I'm going to try and give a sense of what that has to do with the future of the world. First word, zoonosis. Very easy to define. A zoonosis is an animal infection that's transmissible to humans. Excuse me. Hay fever, I don't think I'm carrying anything. A zoonosis is an animal infection that's transmissible to humans. It might be a virus like Ebola or the SARS coronavirus. It could be a bacterium like the one that causes Lyme disease. It might be a fungus or a worm or a protozoan, like the bug that causes malaria. That's a protozoan. It might even be a prion, like the strange folded protein phenomenon that causes Creutzfeldt-Jakob and mad cow disease. All of those are the categories of infectious agents. But whatever it is, whether it's a virus or a bacterium or a protozoan, once this thing gets into humans, if it causes illness, it causes symptoms, takes hold, spreads, we call that a zoonotic disease. Zoonotic disease. Now, this is not a small subject at the weird fringe of medicine. It's central, and its applications are big. About 60% of the infectious diseases known among humans fall in this category. They're zoonotic diseases. And that includes some of the most infamous old ones, like bubonic plague, as well as some of the scariest and most mysterious new ones, like hantavirus, pulmonary syndrome. These zoonoses, these animal infections transmissible to humans, for all their bad effects, in my view, they serve one valuable purpose. They remind us of the connectedness between humans and other species. And one form of that connectedness is shared disease. Animal disease, human disease, same disease in these cases. So just thinking about these things, just thinking about zoonosis, tends to reaffirm the old Darwinian truth, and I think of it as the darkest and most difficult, ultimately, of Charles Darwin's truths. The old Darwinian truth that we humans are animals. We're part of nature. We're not separate from it or somehow above it. That seems obvious. It seems like a truism, and yet it's so easy to forget. Zoonotic diseases help to remind us. There are a lot of new entries to the gruesome list of zoonoses. Most of them are viruses. They've emerged and caused outbreaks one after another over the past 5 or 6 decades around the world. Machupo emerging in Bolivia, 1961, emerging from rodents in Bolivian villages, killing people. Marburg virus, which is related to Ebola virus in the same family, coming out of Central Africa in 1967, getting to Marburg, Germany, where it got its name. Ebola itself, first hitting the radar screen in 1976 in what was then Zaire, now Democratic Republic of the Congo. HIV, complicated story, but coming to attention in 1981 in a few spots in North America, including Los Angeles. Hantavirus, again, an old disease that was newly brought to our attention in 1993 with a terrifying and mysterious outbreak in the Four Corners area of the American Southwest. Hantavirus. Hendra virus, a mysterious thing in Australia that falls out of bats and gets into racehorses and passes from racehorses into humans, killing the horses, killing the humans. Bird flu, coming out of Hong Kong, 1997. Something called Nipah in Malaysia and then Bangladesh, 1998, another mysterious virus coming out of animals. West Nile showing up in New York City in crows and robins in 1999, killing people too. SARS emerging from southern China by way of Hong Kong to the rest of the world in 2003, and then more recently MERS, originating, we gather, in the Arabian Peninsula, 2012. So over this period of time, it's been a drumbeat of these scary new viruses emerging. But if they're emerging from where? Well, I hinted a little bit at that. Every new zoonotic disease starts as a mystery story, and the biological source of the causal agent, the virus, is one of those mysteries. And that's actually one of the reasons, if you'll pardon the word enjoy, I enjoyed writing a long book, Spillover, about zoonotic diseases, because it's one mystery story after another. And everybody likes to read mystery stories, right? You can turn a gruesome subject into something that actually makes people want to turn the pages, or actually listen to you as an after-dinner speech with full stomachs, because people like mysteries. And the first mystery is, where did this new virus, come from? We can guess that it must have crossed into humans from another kind of animal. But which animal in each case? That's one of the mysteries. Which animal? There's a special term here, too. Reservoir host. Any species in which a zoonotic bug lives permanently, inconspicuously, endemically without causing symptoms, that's known as a reservoir host of the pathogen. Now, usually that means a species of wildlife. Domestic animals, in some cases, have been sources of new zoonoses, but more often it's wildlife. The reservoir host is some kind of a wild animal. Bats, as I mentioned, giant fruit bats are the reservoir host of Hendra virus, that horse and human killing thing in Australia. HIV came to us from chimpanzees. The influenzas, the influenzas that infect humans and make us so sick, all have their reservoirs in wild aquatic birds. West Nile virus, as I mentioned, also has its reservoir host in birds. The SARS coronavirus in southern China, bats again. The reservoir host of Ebola, anybody want to take a guess? I hear bats. I hear some other things. In fact, the reservoir host of Ebola is still undiscovered. You hear people say it's bats, but this has never been confirmed. It's an abiding mystery. There is no really, really solid molecular proof yet that bats or whatever other creature are the reservoir hosts of Ebola. But we do know that Marburg, Ebola's cousin, as I mentioned, does have its reservoir in a species of large African fruit bat. Now, I promised stories as well as facts and definitions, so let's go back pretty quickly, I hope, to Ebola. You know the facts, the numbers. You saw those in the news all last year, and I've recounted some of them. You may not know, let me see. You may not know that the Ebola outbreak of 2014 began in one little village of southeastern Guinea in December of 2013. The index case, the first known infected person, was a little boy, a toddler, in this village. This is the village, a village called Meliandu in southeastern Guinea. And this boy got sick and died, feverish, in December 2013. Sadly, it's not unusual for children to die of unexplained fevers in villages in Central and West Africa, so people didn't think too much of it. And then his mother died about a week later, and then his grandmother died, and then I think his sister died, and a nurse in the same village died. And it became clear that something nasty was going on. But it wasn't until March of 2014 that the word Ebola was spoken, when they finally got some samples. By that time, this phenomenon, whatever it was, had spread through that village to several other villages and was making its way from the villages of southeastern Guinea to the capital cities, where it became devastating. An Ebola outbreak had never really struck hard in a capital city before. Most of the previous outbreaks had occurred in the Democratic Republic of Congo, elsewhere in Central Africa, not in West Africa. In most of those places, it was a phenomenon that occurred in remote villages and killed a few dozen people, in some cases a few hundred people, people who were so poor and so remote that they weren't getting to capital cities, and they certainly weren't getting on airplanes. So it was possible to stop those earlier Ebola outbreaks, which was done. Most of them were contained before they had reached 300 fatalities. There's no treatment, at least until recently, there was no treatment for Ebola virus disease, as it's called. All you could do was give supportive care, give fluids, give some general antibiotics. Why antibiotics against a virus? Antibiotics are no good against viruses, right? Yes, but there were secondary infections with bacteria in some cases, and you could perhaps help people by giving them antibiotics against the bacterial infections. But you really couldn't do much except isolate people, separate infected patients from their loved ones, from other people in their communities. This man is not being lowered into a grave. This man is being brought back after having charged out of an Ebola treatment center in West Africa and tried to climb over the concertina wire in the back of the place, and then had to be brought back in by these healthcare workers. This was in Sierra Leone, and this amazing photograph was taken by a fellow named Pete Muller, who's one of my colleagues at National Geographic. He and I worked on an Ebola story together this time last year. It ran in the July issue of National Geographic. This is another of Pete's photographs. So 28,000 cases, of which 27,999 were cases of human-to-human transmission, and one was an animal-to-human transmission. And we still don't know from which animal. But there has been some suspicion that it was a bat, and that it was a kind of not a giant fruit bat, but a small insect-eating bat that lived, among other places, in this hollow tree. This is a hollow tree, again a photograph by Pete, hollow tree in the village of Meliandou. It was suspected, perhaps, that the index case, that little boy, along with his playmates, had played in this hollow tree where there were all these bats roosting, and that he might have picked up an infection if those bats were carrying it. Pete and I went to West Africa, went to Ivory Coast, not to the outbreak countries, with a German team to investigate that hypothesis last November, just about this time. A wonderful German scientist named Fabian Leendertz, who was investigating that possibility. So far, the results are negative. That species of bat is just another on the list of possible Ebola reservoirs that hasn't been confirmed. So, as I said, 27,999 roughly cases of animal-to-animal transmission, human-to-human transmission, one animal-to-human, and that event is what we call a spillover. When a zoonotic bug passes from its reservoir host into its first human victim, that's the moment of spillover. Now, spillover happens because of opportunity. Let me go back to this for a second. Opportunity. The virus gets an opportunity to cross from its reservoir host into a new host, such as humans. And why does that opportunity occur? It happens because people come into close contact with wildlife, as they do in forested areas of Central Africa quite frequently. They might be killing and eating wild animals. We call that bushmeat when Africans do it. We call it game when people in Montana do it. They might be trapping wild animals and transporting them live to market for sale. They might be keeping wild animals as pets. They might get bitten or scratched by an animal that they encounter in their house, in the thatched roof of their house, or in their attic or their garage in California or Montana. They might be raising livestock in such a way that their domestic animals have contact with wildlife, picking up viruses that are then passed along to people. Case in point, Hendra virus, horses to humans in Australia. Or they might simply be sweeping up dust in an old shed. And if that dust has been seasoned, for instance, with dried mouse urine, and the mouse happens to be carrying hantavirus, then the person sweeping might inhale some of that. And the mouse-borne hantavirus gets an opportunity to take hold in human lungs. But opportunity alone isn't enough. When there's spillover, evolution also comes into play. If the virus is highly adaptable, if it mutates quickly, changes quickly, adjusts well to new circumstances, then it's all the more likely to succeed as a zoonotic infection. Natural selection occurs. An animal virus becomes a human virus. And if it adapts in this way and gets itself transmitted from one human host to another, then that particular virus has vastly increased its evolutionary success. Getting into the human population for a virus is like winning the sweepstakes. So now you've got the basics, the first three crucial ideas and the key terms: zoonosis, reservoir host, spillover. With that much, you all now understand more about the dynamics of infectious disease than 99% of the human population. So pat yourselves on the back and get a flu shot this autumn. But why are all these spillovers occurring? Why are some of them quickly circling the world? I can answer that with two further words: disruption and connectivity. More and more, I'm telling you things you know, but I'm highlighting them. We humans are disrupting all of the wild, diverse ecosystems that harbor so many different kinds of creatures: animals, plants, fungi, bacteria. And each of those kinds of creatures in those highly diverse places, scientists tell us, are harboring unique viruses. Each species of animal, plant, fungus, bacterium might be harboring 10 unique species of viruses. There's lots of viruses out there, folks. And all of our logging and burning and road building and settlement and killing and eating of bushmeat, all of those actions shake loose new viruses from their hosts, offering them opportunities to infect humans instead, because we are there. We're doing that. Disruption. And once they infect us, once they get into us and adapt and find ways to transmit from human to human, then they can travel at the speed of an airplane, not just a sailing ship anymore. If transmission is really efficient and if virulence is high, then this new virus might kill millions of people along the way, circling the world and doing it quickly. That's connectivity. Now that brings me to story number 2. It turns out that the story of the ecological origins of the AIDS pandemic is very different from what we thought we knew, what we all thought we knew about the beginnings in the 1980s and the promiscuous Canadian airline steward who was traveling around having gay relationships in a lot of different towns, and it was being spread in the gay community that way. That was not the beginning, and that guy was not patient 0. He was patient 684,250. We now know from good, persuasive molecular genetics that have been done over just the last 15 years that the AIDS pandemic began a lot earlier than that and in a very different way. We know that the pandemic strain of HIV, which is one of several strains of HIV, but the pandemic strain, the one that accounts for almost all of the, 36 million deaths so far around the world, that pandemic strain, HIV-1 group M, passed from a single chimpanzee to a single human in the southeastern corner of Cameroon, Central Africa, back around 1908, give or take a margin of error. It happened there. Southeastern corner of Cameroon. And then it simmered quietly, undetected, unsuspected for decades in the villages of southeastern Cameroon, passing only barely to one new victim from each infected person, so that it barely stayed alive as a chain of infection. probably then working its way down the river system, out of southeastern Cameroon, down the Ngoko, the little Ngoko River, to the Sangha River, and down if I had an electronic pointer, I probably do. Oh, I haven't even been using this thing, and Brian gave it to me. Wonder if there's an electronic pointer. Anyway, oops. Oh, now I've done it. There's the electronic pointer. Okay, that helps a lot. Brian, can you? So it started here, and then it moved down here, and then it got to the main stem Congo River, and it got to these big capital cities here, Brazzaville, and what then was called Leopoldville, the capital of the Belgian Congo. You all have good imaginations. You listen to the radio, NPR, right? Oh, I just hit it again. Oh, man, thank you. All right, so there we are. Yes. Brian. I'm going to leave well enough alone now. Anyway, so it worked its way downriver to these capital cities, and then sexual mores were different, population density was different. There were injectable drugs being used for treatment of venereal diseases, for malaria, for sleeping sickness, trypanosomiasis. And in those days, injectable drugs were not delivered in disposable syringes. A needle and syringe was a precision medical instrument, and so they were rinsed and reused. There was one doctor in the French Congo in the 1920s who treated something like 6,000 people over the course of about 4 years, 6,000 different victims suffering from trypanosomiasis using 6 syringes. Now, we don't know that this was one of the most important factors helping the AIDS pandemic to get going, to take hold, but it's highly probable that it contributed to it. So then it got to the capital cities of Brazzaville and Leopoldville. Leopoldville became Kinshasa with Congolese independence. The Belgians were sent home. The Congolese needed help because they had no professional class. They had no engineers, no doctors, no lawyers, no civil servants, because the Belgians hadn't trained any Congolese to hold those roles. So UNESCO asked for help for the Congolese people in what now was known, at that point, Democratic Republic of Congo, then it became Zaire, and then it became DRC again. They needed help, and who sent help? The Haitians. Does that ring a bell? Early on in the AIDS pandemic, we heard that there was some connection to Haitians. The Haitians went to the Democratic Republic of the Congo. They helped the Congolese get on their feet at independence. They had Haitian wives, girlfriends, boyfriends, and somebody picked up the infection and took it back to Haiti in the mid-1960s. And from Haiti, it got to the U.S. one way or another. I talk about this in Spillover and in the short book, The Chimp in the River. And then in the U.S., it spread through several different communities, through the gay community, through the community of people using injectable drugs, through the hemophiliac community who are dependent on blood products, et cetera, and that brings us up to the 1980-81 period that everybody has heard about. But there was this long, tragic ecological history to the story before that. I would say more about that, but I don't want to go over my time. So I promised one more definition, outbreak. There's a definition of outbreak within the world of public health and infectious diseases. That's the one that we've been thinking about tonight. An outbreak is a smallish cluster of cases of an infectious disease in which maybe dozens or hundreds of people become infected. And then if luck is bad and the rate of transmission is high, then an outbreak may grow into an epidemic, an event on a national scale. And if luck is still worse, the epidemic becomes a pandemic circling the world. But that's not the definition that I want to talk about. There's a very distinct definition of the same word, outbreak, within the field of ecology. And remember, I've been trying to highlight the fact that this is really an ecological subject. So outbreak in the field of ecology. A population outbreak, in ecological terms, is any huge sudden increase in the abundance of one kind of creature, in the abundance of one species. And certain kinds of insect have this capacity. For instance, the gypsy moth, the spruce budworm, those are forms of Lepidoptera, butterfly and moth, that are particularly important in infecting forests. And this critter, what we call tent caterpillars, which are another kind of moth, a forest-infecting moth. Tent caterpillars feed on leaves. The caterpillar phase of the moth does, and they have really high intrinsic rates of reproduction, each female laying hundreds of eggs per clutch. And in a normal year, most of those eggs might hatch, but the little tiny caterpillars would probably die. Every so often, there's an exceptionally good year for a creature like tent caterpillars. And that means there's plenty of food, the weather is just right, the moisture level is just right. Everything is ideal so that the hatch rate is very high, survival of the little caterpillars is very high. They grow up and they pupate and become moths. And there might even be multiple generations of tent caterpillar in a single summer. So as a result of that, you get this sudden population outbreak. Everything is ideal, everything goes right. Reproduction potential is high, mortality is very low, and suddenly you get zillions and zillions of tent caterpillars. You get this abrupt population increase by orders of magnitude. Suddenly these things are everywhere, and they eat up everything. They eat all the leaves off your trees. And it seems as though they're going to kill this forest. But in fact, they haven't necessarily killed the trees. The trees can put out leaves a second time that summer. The trees can survive, usually, if they're lucky, if the outbreak doesn't go on, if the pressure doesn't continue year after year. And usually it doesn't, because the thing about an outbreak of this kind of an animal, an outbreak population, is that these outbreaks end. And usually they end as abruptly as they began. So after just 1 year or maybe 2 years of this pestilential abundance of tent caterpillars, the population crashes. The tent caterpillars disappear, no longer a problem. You don't have to spray for them. You don't have to go out and take drastic chemical measures to get rid of them. They've disappeared. They haven't gone completely extinct. They're lingering as a remnant, an inconspicuous remnant population in the forest in question, but they've died way, way back from their former population level. They're relatively scarce until the next outbreak. Now, most people, when they hear about these outbreak cycles, are inclined to say, oh, okay, yeah, I know why those populations crash. I've read Jared Diamond. It's because they have eaten up their entire food supply. They have eaten themselves to the point of starvation. And in fact, that's not the reason. There's another factor that usually kicks in before the level of starvation, somewhere short of that point, when they die because they have destroyed all their resources. There's a different factor that causes these crashes. Anybody want to guess? Viral infection. The ecologists who study forest Lepidoptera have discovered that viral plagues are what cause these populations to crash. And in particular, there's a group known as the nucleopolyhedrosis viruses, NPV for short. This will not be on the quiz at the end of the talk. That cause these crashes in forest Lepidoptera, in the caterpillars. These viruses are always present, again, at very, very low levels in the populations, so that there is a potential. And usually they're not a big problem, but when a population outbreak of the caterpillars occurs, so that you've got these zillions of caterpillars living together in these dense aggregations, hundreds on a little twig, and sometimes inside a silk tent, like the silk tent I showed earlier, in that confined space, that hermetic environment, then conditions become perfect for a viral plague. So one caterpillar becomes infected, and it fills up with virus, and it literally, I mean, disgustingly, fills up with virus. So you've got this caterpillar, and it looks normal, maybe a little puffy, and it's crawling its way across an elm leaf, chewing its way happily across an elm leaf, and it bursts open like a water balloon and leaves a smear of virus on that leaf, and that's all that's left of it. And then another caterpillar comes chewing along happily across the same leaf and chews its way through that smear of virus and becomes infected, does the same thing, passes it to the next caterpillar, etc. And you've got this cascade. You've got this crash, this pandemic of this virus among these caterpillars. If the transmission is really high because of that kind of situation, and the virulence is high, which it is, then bingo, the insect population crashes. Now, why am I bringing this up? Well, it's because we humans, in ecological terms, are an outbreak population. And this is not a notion I invented. This is what ecologists, including ecologists who study forest Lepidoptera, say. There was one fellow, Alan Berriman, writing about the theory and classification of insect outbreaks, who said, from this perspective, the most serious outbreak on the planet Earth is that of the species Homo sapiens. So we, of course, reproduce more slowly than forest insects. But now that we've built up such a huge head of steam, there are 7 billion of us, the annual increments of increase are huge, and we are an outbreak population. There has never been, and we know this from the fossil record, there has never been a single species of large-bodied vertebrate animal on planet Earth anywhere near as abundant as we are now. We know that from the fossil record because it would be clear in the fossil record if anything had been as abundant as us in the past. We're an outbreak. I don't want you to think I'm a misanthrope. I mean, I probably am a misanthrope, but I don't want you to think it just on this basis. I mean, we are a wonderful species, humans, in many ways. We're capable of music and generosity and grandmaster chess and Major League Baseball and iambic pentameter, but we are an outbreak. So what's the logical inference? It's that we humans face the possibility of a catastrophic population crash like any other outbreak population. And corollary to that, if that happens, if that population crash happens, the cause might very well be a virus, not NPV virus, but one of our own. We know that the influenza virus of 1918 killed 50 million people. HIV has now killed almost 40 million people. It is not just possible, it is entirely plausible. This parallel between insect outbreaks and our current human population is what I call the analogy. And I'm going to end with with a little bit of wisdom from this fellow on the analogy. This fellow is a man named Greg Dwyer. He studies outbreak cycles of forest Lepidoptera populations, including tent caterpillars and gypsy moths. He's at the University of Chicago. And as I was finishing the research for my book Spillover, I went to see him to ask him about the analogy. Is it likely that, first of all, are we an outbreak population, humans in the same sense? And if so, do we almost inevitably face that kind of a viral-caused crash? And I asked him that, visited him at his lab, and he thought about it carefully. And he said, yeah, the analogy is valid. He agreed that we are an outbreak population. And then the second part, does that mean we inevitably face that kind of a crash? And he thought about it very carefully. He said, wait a minute, give me a little time. Now, Greg Dwyer is a very smart guy with a good sense of humor. He's serious and judicious, but a little bit whimsical. He thought about my question for about a half an hour as he toured me through the lab, and he stood at his whiteboard with a Sharpie, and he drew elaborate mathematical equations representing some of his models on the whiteboard, and I stood up and walked over and stood near him to make it seem like I understood what he was saying. And he talked me through all this, and then finally he explained his models, and he has all these parameters that go into his models that shape the outbreaks that happen and the crashes that happen. Mathematical modeling, you put in parameters of different sorts, and you turn the crank and you get a result. And the parameters would include things like the density of the host population, the virulence of the virus, and he also mentioned one other, heterogeneity of behavior. Heterogeneity of behavior. I almost had a slide with that. I don't think I have a slide with those words on it, but he said that's very important in the fate of these crashes of outbreak populations, heterogeneity of behavior. If there is some flexibility, if there is some variation, if there is some ability to be different, one individual from another, then it has an important impact on how the crash proceeds, how the epidemic or the pandemic proceeds, whether the crash is very sudden or whether the decline of the population is gradual. Heterogeneity of behavior. So for instance, caterpillars crawling across the leaf, and there's a smear of virus, and either the caterpillar goes through it, or possibly the caterpillar is capable of going antennae, detection, suspicion, doesn't seem right, and it chews its way around. It chews itself in a different direction. That is heterogeneity of behavior. Very important, said Greg Dwyer, in the shape of the curve of the end of the catastrophic infection, whether it's a gentle decrease and less catastrophic, or whether it is a total crash. And then he pulled all this together in his mind, and he went back to my second question about the analogy. Is it inevitable that we will crash due to a catastrophic viral epidemic? And he thought about it very carefully, and I waited. And he said, no, I don't think it's inevitable. I don't think it's inevitable. Why not? Because we humans have heterogeneity of behavior. And my models, he said, show that that is crucial. We humans are capable of learning. We're capable of adaptation. We can adjust. We can change our ways. We can understand the threats against us and take steps to protect ourselves. I did have the slide. That's important. That's crucial, said Greg. And that's the expert wisdom that I offer you tonight, direct from the world of mathematical forest ecology. We humans aren't necessarily doomed to suffer a catastrophic crash, according to this thinking, because we're smarter than tent caterpillars. And that's the good news. Thank you very much.
We now have time for questions. If you have a question, please raise your hand and wait for Henrietta or I to come to you with a microphone. As always, priority will go to students.
So I actually have two questions. First question is, so we have a choice in who we vote for presidential elections, and I'm wondering if there's a candidate on this issue that is better, in your opinion, than other candidates. And my second question is, so I heard that one of the patients that had Ebola, they thought she was cured and now had a relapse, so just kind of curious what the latest is on that.
Yeah. Okay, first question first. Is there a candidate who's better on this than others? Well, nobody has asked this question at any of those debates, and it seems, well, I think it's a little bit more complicated than the environment. I think somebody should be asking these candidates, how do we assimilate the lesson of 2014? The crazed Ebola scare of 2014. Yes, it has gone away. At least it's gone away from America. We're not worried about it. Does that mean we should forget about it? No, that means that now we have an opportunity to prepare for the next one. What would you do? Nobody's been asked that question, so we don't know who would give the best answer. But anybody who says the CDC has too much money is not that person. As for that, the woman, the Scottish nurse, I can't remember her name, Cafferary or something like that. I haven't heard the latest, but I gather she's past the crisis. I hope that she is and that she's going to live. We're learning things. We're still learning a lot about the way Ebola works. We don't know where it lives when it's not killing humans. We don't really know how it affects the human body. And we certainly don't know how it can go dormant in a human body and then come back 9 months later. That's been seen with some of these other viruses. But she and the fellow who was discovered to have Ebola lingering in his eye, I don't know if you heard about that, are two new data points that are defining a completely new trajectory on the curve of what Ebola is capable of doing. We really need to know a lot more. The hard thing about Ebola is that when there is an outbreak, then everybody wants to spend money to deal with the outbreak, and when the outbreak is over, nobody wants to spend money to deal with it at all.
Hi there, my name's Dan. We heard in your introduction that you wrote some fiction novels, and I was wondering what were some of your favorite books that you've written and what kind of themes you explored in those.
Well, I've had a long, improbable and disorganized career. I began as a novelist, published my first novel back in 1970 when I was just out of college, and then I discovered that the world didn't need me to be a novelist. And I paid my dues between my first book and my second book, so 13 years passed, and I did the usual things that young, starving writers do: tend bar, wait tables, work as a fishing guide, all that sort of thing in Montana. It was very, it was healthy, it was salubrious to have that period of time. In the course of that, I turned into a nonfiction writer with a particular interest in the biological sciences. When I was a fiction writer, I was obsessed with William Faulkner. So when I write a book like The Song of the Dodo or Spillover, which is a complicated scientific nonfiction work which is intended to be very engrossing and entertaining as well as serious, the chief influence on that piece of work is probably William Faulkner and the novels of William Faulkner. My own favorites among my own work, it's always the most recent, so I guess Spillover and the two little books that came from it. But thank you for asking that.
Hello? Hi, I'm over here. With regards to Spillover, do you think that we can keep up with population gain and our ways to prevent spillover? Wait, no, sorry, not spillover, but the connectivity problem that you were talking about?
The connectivity problem, yeah.
Yeah, how can we keep up with preventing more rapid connectivity of viruses throughout our globalized population with population increase as it goes right
Well,
now?
that's a big, useful, complicated question, and I'll just say one thing. We're fortunate that information travels even faster than jet airplanes. So there now is a great deal of instantaneous connectivity among the scientists around the world who study this stuff. And there is an explosion in ingenious tools for viral discovery, viral identification, characterization. So we're getting to the point where, as the threat increases, our ability to deal with the threat also increases. There are inventions in electronic molecular diagnostic forensics, I don't know exactly what you would call it, such that before too long, you'll be able to be screened for a virus when you go through an airport almost as quickly or maybe more quickly than they can x-ray your carry-on bag. And you'll step through the TSA checkpoint and they will tell you, well, I'm sorry, Mr. Quammen, but you're carrying influenza, or you're carrying Ebola, dude. Go over there. That's coming. And in some ways that's very good, but that will also raise questions in civil liberties. So there are complicated decisions to be made as to how we employ our resources, how we employ our heterogeneity of behavior that involve human rights, civil liberties, as well as safety of the herd. The most crucial thing that can happen in the meantime is that people start to understand this better from the ground level up. And that's what I've been trying to do in things like Spillover.
Hello, thank you for your talk. Because there are so many definitions of life, I was wondering if you considered viruses such as Ebola to be alive.
A classic conundrum that virologists and other forms of biologists are still arguing about: are viruses alive? And it's a useful question, but it's almost like a Zen koan. You know, it's one that doesn't have any perfect, satisfying answer that's easily arrived at. It depends on how you define life, whether a virus is alive or not. And it might not be important even to be able to put those words to the question. We have some idea how viruses work. They are these molecular gizmos that are in some ways very lifelike, but they can only replicate themselves inside the replicating machinery of a living cell. They're not cellular themselves. So that's what they are. I think the more interesting question even than are they life or not is, where did they come from? How did they evolve? Did they evolve before cellular life? Did they break off from cellular life? Or what? That's a really interesting question, and it's something that is on my reading list right now for my next book project. I'm reading scientists who work on the origins of life and the origins of cellular life, how viruses fit into that. Really complicated, interesting stuff.
Hi, I'm Emily. Thank you for the talk, by the way. I have a question about whether you've done any research concerning weaponization of viruses or like biological warfare of them.
Mm-hmm. I've read a bit about that. It wasn't a major part of my research for Spillover, but it's certainly part of the larger subject. The Department of Homeland Security, for instance, spends a lot of money on Ebola. I have a friend who was an Ebola vaccine researcher who was working on a $5 million contract from the Department of Homeland Security. This was, 8 years ago, to develop an Ebola vaccine. And then you say, well, okay, if the Department of Homeland Security wants an Ebola vaccine, what's the intended use? Who are they going to give that to? Are they going to vaccinate everybody in Central Africa? No. Presumably they're going to vaccinate the responders at the CDC and other things. Maybe they're going to vaccinate the people at the TSA checkpoints. Don't know. the weaponization of these viruses is certainly something we have to be concerned about, and yet I don't think it should be the greatest concern, because it doesn't take a terrorist to spread a new virus to a new continent. That can be done by a migrating bird. It can be done by an animal that somebody is bringing back as a pet. It can be done by a piece of monkey meat in a container that's secretly shipped from the Congo to New York. So I can't say much more about it than that. You could find a shelf of books to read on the subject of that. It's, as I say, it's part of the larger problem, but I don't think it's the greatest aspect of the threat that viruses pose to us, or the greatest aspect of the threat that terrorists pose to us. It's not the most efficient way to kill people.
Thank you. Could you say a little bit about your own, well, I'll say research methods? In the Chimp across the river, you describe a trip that you're taking with some people who are trying to find gorillas, and you're talking with people who are relatives of those who have died of Ebola. And I'm reading this and I'm thinking, are you crazy? You're taking such a risk. Could you talk about that?
I don't think of it as risky at the time. I love going. One of my cardinal principles as a nonfiction writer, I've got a whole list of them, sort of semi-facetious cardinal principles, and one of them is go there. Go there. Go get your feet dirty. Talk to the people. See the place. Sniff around on the ground. And so I went, in researching Spillover, including the Chimp in the river, I went to a lot of places around the world with scientists who were looking for deadly viruses and hoping that they would find deadly viruses, capturing bats in a cave in southern China, or capturing bats on a rooftop in Bangladesh in the middle of the night, or trying to tranquilize gorillas in the Congo to take blood samples, or whatever. My operating procedure is that I stand about 4 feet behind the scientist when he's taking this blood sample, or when she is handling this perhaps infected animal, and try and keep my hands behind my back and stay out of the way, and hope that they don't say, "Here, hold this bat," which occasionally they do, but usually not. And these people that I travel with, these scientists, they're not suicidal, they're not crazy, they're knowledgeable, they're cautious, they love life. And so I take whatever precautions they take, plus another healthy layer. So far, I've been fine. And my wife sometimes says, you're doing what? You're going where? To do what? And you're going to fly in another one of those small planes across the African forest and go look for animals carrying viruses? And I reassure her, honey, bear in mind that the most dangerous thing that I'll do is get in the taxi cab from the Kinshasa airport to the hotel. After that, nothing is nearly as risky.
Hi, thank you for your talk. At one point, you sort of said, pardon my use of the word enjoying, and I was curious, it made me think about if you feel any responsibility to be careful with the language you're using or the way that you present some of this information, which is about millions of lives lost and sort of very tragic circumstances. If you feel sort of a responsibility to handle the material in a certain way, or if that's a challenge you faced, I'm interested to hear you sort of talk about that.
Yes, thank you for asking. I absolutely do. I have huge respect and passionate sympathy for people such as the people in Central Africa, in those villages, who suffer these diseases. And I have huge respect for their situation. And I try and show that in the way that I write about them and talk about them. And at the same time, there's a streak in me that just says nothing is too serious to be written about completely without humor. I think that humor is hugely important in coping with sorrow and coping with misery and coping with complicated scientific information, in getting people to turn the pages. So when I write something, my ultimate hope is that this is a magazine piece or this is a book. I hope that on one page will make people cry, 20 pages later will make them laugh out loud, and at the end of the book will cause them to say, oh, now I see the world in a slightly different way. So that's what I'm after. I'm a smart aleck, I'm afraid, but a respectful one.
Hi, thank you very much. It seems like all the viruses that I've heard about, the West Nile, SARS, the Ebola, they've all just been, they came and they went. They never really spread. But the AIDS virus seemed to spread and killed so many people,
Right.
a lot of people I knew. And I just wonder why it affected them and why we didn't have the cure. You know, it just seems like it was kind of, they were aced out, or they were kind of like attacked.
Well, I'm not sure how to answer that. I mean, there are I hear you making a passionate statement, and I agree with it. And there is no answer to that passionate statement. On the scientific level, why has the AIDS pandemic been different from Ebola or SARS or influenza? There are a couple of different reasons. One is that HIV is a very patient, subtle, insidious virus that moves very slowly but kills relentlessly. At least it did until the drug cocktails became available. So that by the time we realized that it existed even, millions of people were infected. Ebola is not at all like that. It's not subtle, it's not patient. It goes crash, bang, and splashes blood around and kills people fast. It doesn't always splash blood around, but anyway, it's very different. The influenza of 1918, I mentioned, killed 50 million people around the world, killed even more people than have died so far from AIDS. The influenzas spread very quickly. It's also an impatient kind of virus. It's not nearly as lethal as HIV or Ebola or rabies in terms of the percentage of people killed, but it spreads so quickly and it changes so much from year to year that it remains one of the major public health threats in the world. There could be an influenza epidemic next year that killed 10 million people around the globe. It wouldn't be at all surprising if that happened. AIDS is especially a hurtful, tragic, sad story for a lot of reasons. But one of them is that it was a completely new kind of very subtle, patient, insidious virus.
Good evening. I remember once watching CNN and seeing the caption on the bottom of the screen read Ebola, subheading the ISIS of diseases, ? And I was wondering if you could speak to the media perception and the way it portrays viruses and what kind of reforms you would like to see in it.
I didn't see that. I hadn't even realized that ISIS had emerged to be that conspicuous, to be called was it Ebola was the ISIS of diseases, or ISIS was the Ebola of political movements? Anyway, the news media always are looking for dramatic simplifications. I mean, I'm part of the journalistic estate, so I am talking about my own colleagues when I talk about this. But I was also involved in that last year, involved in the Ebola media coverage, because I had published these books about Ebola, and so I was one of the people on the Rolodex, one of the talking heads that they called up, and kept asking me, well, will you come on this show or that show? Anderson Cooper, China Central Television, whatever, and answer some questions about Ebola. And I was happy to do that because I wanted to marginally, if I could, incrementally, increase the level of understanding and decrease the level of hysteria. But it was hard to do. I usually didn't get asked the question that I wanted to be asked. I got asked something that I shouldn't have been answering, and then the question that I wanted to answer, nobody got asked. It was not the news media's finest hour, but it didn't really teach us anything about the news media, particularly electronic media, that we didn't already know, which is that the news television shows sell drama first and enlightenment second. I shouldn't say that as a blanket statement. I did a few nights on Anderson Cooper's show. He was trying for an intelligent discussion, but there was never enough time. There was never quite the right questions, and he had pressures on him. Likewise with the other people that I did interviews with. There are always these pressures because these are businesses, and people have short attention spans. So you need to deal with the question you're asked and answer it in about 20 seconds. And it's not a recipe for spreading depth of understanding. But thanks for asking that, Austin.
I have a question myself, actually.
Yes, Shwen.
From your presentation, I have a question about the analogy. It seems that the implication is that when there's an outbreak population, there is a higher possibility of a virus wiping the entire population out. So I was wondering if there were other species where there was an outbreak in terms of numbers that this happened, or were there also smaller species where a virus wiped the entire population out as well? So I'm kind of unsure about whether it's a correlation or a causation kind of thing.
Well, there are, as I mentioned at the beginning, every kind of animal, plant, fungus, and bacterium on the planet is infected with viruses, and viruses that are unique to it. Some of those are passenger viruses that have no effect, just as we have passenger viruses that have no effect on us. And some of them are pathogenic viruses that cause crashes. And those things probably always go in cycles, but the extremity of the cycles depends on a couple of different factors, as Greg Dwyer explained to me. Depends on the life history pattern of the infected species, what its reproductive rate is, what its breeding habits are, what its behavioral patterns are, what its living conditions are. It depends on the virulence of the virus. It depends on the transmissibility of the virus. It depends on some other even more complicated things like with humans, say that not just the transmissibility and the virulence, but at what stage do humans become infectious with a particular virus. One of the things that was dangerous about SARS was that people became very infectious and capable of spreading SARS while they were still healthy enough to be walking around, going to work, riding the subway. That's different from Ebola. By the time people become infectious with Ebola, they're lying on a cot, with a horrible fever, and everybody knows they're sick. They're not going to work. So all of those factors for us as a victim species or for any other creature are what affects the cycles of viral infection. And I can't think of any other good examples right now, but you could name any population. African lions had a terrible affliction with a new virus about 15 or 20 years ago. It was a canine distemper virus that had been brought into the Serengeti, probably in a dog, and it mutated so that it could become a feline, not canine distemper virus, and it started killing the lions of Africa. And it killed something like 90% of the lions of the Ngorongoro crater in a couple of years, and a large proportion of the lions on the Serengeti. And then it wasn't so bad anymore. The outbreak ended, partly because Probably mainly because the most susceptible lions had become infected and had died. The ones that survived had some natural resistance. Maybe the virus mutated also. Anyway, the problem went away. It's not a crisis anymore. So there are stories like that in virtually any species you could name.
That's all the time we have for questions tonight. Please join me in thanking Mr. David Quammen.
Thank you all very, very much. I really enjoyed this. You're a great audience, great people to have a conversation with.